So we shall learn about center of mass, or abbreviated as CM. So center of mass of a system of particles. Okay, so we will define the location of center of mass in the following way. Suppose these dots are particles, say particles of mass, this M1, M2, M3, M4, and like that. And suppose this is a system, and with respect to a certain coordinate system, these position vectors of the particles, say m1 position vector is r1, say m2 position vector is r2, and say m4 and m3 all position vectors are 3 r4, like that. So this is actually the system. System is a region in space of our choice actually. So in the system, the particles of the system have masses m1, m2, m3 up to mn, and with respect to a coordinate system, position vectors, say r1, r2, r3, r4, like that, up to rn, r1, r2, r3, r4 up to rn, like that, which is shown in the diagram. Then the position vector of the center of mass is given by the following equation. Position vector of center of mass is RCM, such that m1 r1 plus m2 r2 plus m3 r3 up to this. So n particles divided by m1 plus m2 plus m3 up to mn. So we can write like this: RCM is m1 r1 plus m2 r2 up to mn rn divided by capital M, where this capital M is total mass of the system, where capital M is m1 plus m2 plus m3 up to mn. So we can also write in the following way: RCM is sigma mr divided by capital M, where capital M is sigma m. So this is the position vector of the center of mass. So you can express position vector of any particle in terms of its coordinates. So r equal to x I cap plus y j cap plus z k cap. Same way you can write RCM is equal to x cm I cap plus y cm j cap plus z cm k cap. And as RCM is equal to sigma mr divided by capital M, so we can write sigma m, r means x I cap plus y j cap plus z k cap divided by capital M. So this x cm I cap plus y cm j cap plus z cm k cap is equal to, we can separate the terms, sigma mx by m times I cap plus sigma my by m times j cap plus sigma mz by m times k cap. So that means xcm. So what is xcm then? So xcm is sigma mx divided by capital M. Same way ycm is sigma my divided by capital M, and zcm is equal to sigma mz divided by capital M. So it means that, say, if x1, x2, x3 up to xn are the x coordinates, of m1 m2 m3 like that, x coordinates of m1 m2 up to mn, then x cm is m1 x1 plus m2 x2 plus m3 x3 like that up to mn xn divided by capital M. Capital M is m1 plus m2 plus m3 plus m4 like that, total mass of the system. And we will have similar formulas like xcm for ycm and zcm as well. Now, so this is the position vector of center of mass given by RCM. Okay, now if you differentiate position vector, then what do you get? Differentiating position vector, you get velocity vector, and further differentiating velocity vector, that is differentiating position vector twice, what you get is the acceleration vector. Now, this RCM, let us differentiate with respect to t on both sides. So what do you get? ddt of RCM is equal to, so these all m1 m2 are constants, so that differential will be here, dt plus, I mean the system may be a moving system, so if the system moves, the mass doesn't change but the coordinates change or position vectors change, so the differential will be here as I have done. Okay. So what's actually dRCM by dt? That is, so this is actually velocity of center of mass. So dr1 dt, it's v1, velocity of particle 1. dr2 dt is velocity of particle 2. It's like that. So vcm, so vcm is m1 v1 plus m2 v2 plus up to mn vn divided by m, or we can write m1 v1 plus m2 v2 plus m3 v3 up to mn vn for n particle system is equal to m, total mass of the system, multiplied by vcm. So that, so this is equal to the total linear momentum of the system. The total linear momentum of the system, that is the sum of the linear momenta of all the particles. That means here, as with this respect, you see, with respect to this calculation of linear momentum, center of mass represents the whole system, right? Center of mass represents the whole system. Now, the net external force on the system of particles is given by the following expression, right? You can refer to lecture number 1 on momentum. So this is actually what we call the Newton's law for a system. Now, so you see here mvcm, whatever we got. So mvcm equal to m1 v1 plus m2 v2 up to mn vn. Right. Now, if you differentiate on both sides, so this ddt on vcm, you get ddt on v1, ddt on v2, and up to ddt on all the velocity terms. So what you get as ddt of vcm is acm. So acm is acceleration of center of mass. That is equal to m1 a1 plus m2 a2 up to mn an. So that means, therefore we can conclude that F equal to MACM. So here also, to apply Newton's law, that center of mass represents the whole system. This is because this is see, suppose for a regular body, say regular body, a disc or a sphere like this, after you calculate center of mass, we will be shortly calculating center of mass. So that is the midpoint. Regular bodies, it is the geometrical center. So if you apply a force at this end, like this F, this is the only external force. So what will the body be doing? So it will be translating and it will be spinning also, right? So every point on the body will have different accelerations, every point having different accelerations. But so the acceleration of center of mass you can calculate from Newton's second law. So ACM is acceleration of center of mass. So we can write F equal to m times ACM. See, this rigid body is also a system of particles, right? It is made up of small particles itself. It's a continuous distribution of mass. Same way, suppose you have say a rolling ball like this, a ball rolling on ground. So what happens? It's moving and rotating as well. So every point has different velocities, right? So center of mass is the midpoint, geometrical center. This has VCM, velocity of the center of mass is VCM, and suppose m is mass of the rolling ball or the rolling disc. Then the total linear momenta rather, of all particles, that is the linear momentum of the system. System means whatever is made of many particles. Particle is a point mass, it is dimensionless. So the linear momentum of the system is given by m times VCM. Right, I'll put a vector sign here, m times VCM. Here also I can put a vector sign, F is equal to m times ACM. Now we'll locate the center of mass actually. We'll locate the center of mass and see. So our next challenge is to locate the center of mass. So by the way, what we have learned is that till now, that center of mass, if you define the position vector of center of mass in the following way, RCM equal to sigma mr divided by m, then what you get, VCM is equal to sigma mv divided by m, and ACM is equal to sigma ma divided by m. So we have that total momentum of system say P for momentum is equal to m times VCM, and the net external force on the system F is equal to m times ACM. Now we will learn to locate the center of mass of a system. The system may be of two types: discrete system and system with continuous distribution of mass. So by a discrete system, say I'll take a very simple example. First, I'll consider an x-axis like this here, and we'll find out the x coordinate only, right? Linear like that system. So this is the 0, and suppose you have masses. So discrete means this separated this point particles, that's say m1, say this particle is m1, that is m2, that is m3, and these are having some coordinates, say x1, and this is having coordinate x2, and say this is having coordinate x3. So we have to locate center of mass of the system. So by the formula, xcm equal to m1 times x1 plus m2 times x2 plus m3 times x3 divided by the total mass m1 plus m2 plus m3. So it will be somewhere, maybe somewhere around there, right? Somewhere on the line. And say if you have a system like this, say this is the x-axis, this is a 0, x equal to 0. Suppose you have two particles, say m, so m1 is also m and m2 is also m. That means say equal mass. So suppose this is x1 and this is x2. So how do locate center of mass here? So xcm is m1 x1, so m1 is x, so plus m2, that is also m, or m1 is m and m2 is m rather, divided by 2m. So xcm happens to be equal to x1 plus x2 by 2. So it is actually at the midpoint. So center of mass is actually at the midpoint. So this is about discrete mass system. So I have shown the x-axis only calculation. Now suppose you have a continuous mass system like this. Say example of a continuous one-dimensional mass system like this, it's a rod. Okay, so this is a rod, and consider a point where this x equal to 0. So how do you calculate here? So here you cannot split it up into particles, right? It's not split it up in it's not an accumulation of particles, discrete particles, as in the case of discrete system. So here what you have to do, at a certain distance x or at a certain coordinate x, you have to consider an elementary and infinitesimally small length dx, and the mass here, so this mass is dm actually. So dm is the mass in length dx, or infinitesimally small mass. And here summation. So actually what is xcm? Xcm is summation of mx divided by m, right? So here for continuous mass distribution, xcm is integration of x dm. See, this m1, m2, m3 masses are like that, these are dm, right? These small masses. So integral x dm divided by m, total mass. So you have to substitute with proper limits. So the target is to do that thing. So divide this rod into infinitesimally small particles like this. Divide this into infinitesimally small particles. So all these small particles each having mass dm, and here this is the formula for continuous mass distribution. xcm is equal to integral x dm by m. So in general, how to deal with a continuous mass distributed system like this? Here you can choose an elementary and infinitesimal small mass dm, and then that's from the coordinate system. With respect to the coordinate system chosen, the position vector happens to be r, and also the coordinates happens to be x, y, and z. Now after you look at the cm is expected to be somewhere there, right? So there you get RCM, right? This is RCM, position vector of CM, and it's having coordinates XCM, YCM, and ZCM respectively. So here you can calculate in this way. So RCM is equal to integration of R, vector R times dm divided by capital M, like this. So the easy way, if you split it up into I cap, j cap, and z cap, because every r, it's x I cap plus y j cap plus z times k cap. So this formula also for individual axis. So xcm is integration of x dm divided by m. Same way, YCM is integral y dm divided by m, and ZCM is integral z dm divided by m. So let's look at some solved problems on locating center of mass of system. Here in this problem, three particles. This is a discrete system. Three particles m1, m2, and m3 has coordinates as given. Find coordinate of center of mass of the system. So we'll apply the formula simply. xcm m1 x1 plus m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. So here what you get is m1 1, x1 is again 1, m2 2, x2 is again 2 plus m3 3 and 2 minus 2 divided by m1 plus m2 plus m3. So what you get, xcm is equal to 2 plus 1 3 minus no, it's not minus 2, plus 2, right? Plus 2, say x1 x2 and x3, right? Okay, so xcm is equal to 3 by 2, and these are all in meter, so 3 by 2 meters. Similarly, you can find ycm as half and zcm as minus half after you put the values. So position vector of cm is given by 3 by 2 times I cap plus 1 by 2 times j cap minus 1 by 2 times k cap. Obviously meter, as all the distances are, all these coordinates are given in meter. In problem number 2, it is the continuous distribution of mass rod of length L. So you have to locate the center of mass and uniformly distributed mass. So we can say let lambda be mass per unit length, This is also known as linear mass density because it is almost a thin rod, so a one dimensional object. So now we'll choose the small mass in the following way. So at a distance x, we'll choose a length dx, and the dm is the mass, right? So dm is the mass of the part of length dx. So now lambda is what? Mass by length. So we can write dm is equal to lambda times dx, right? See that total mass of the rod is how much? Total mass of the rod, capital M, is equal to lambda times L. Okay, so the length of the rod is given as L. Okay, so now let's apply the formula of finding center of mass. xcm is integration of x dm divided by m. So integration of x into lambda dx divided by lambda L. So this lambda will cancel out. So integration of x dx divided by L. So what will be the limits of x? So to cover the entire rod, so that no mass should be left out, so you have to break it up into this small elements like this dx, right? These small masses. So for the here minimum value of x is how much? X minimum is 0 and x maximum is L. This is what you have to choose to cover the entire rod. So the limits I will put from 0 to L. So that means 1 by L. So integral x dx is x square by 2 with the limit 0 to L. So 1 by L. So L square by 2 minus 0 square by 2. So that means you get xm as L by 2. So here, as you see, the center of mass of the rod is located at its geometrical center. In this particular problem, so it's a rod similar to the last problem, a rod of length L only, but the linear mass density is not constant, rather it is a function of x, and as you see x varies from 0 to L. So lambda or mass divided by length depends on x in the following way: lambda equal to kx. Here you have to locate the center of mass. So here, so again I have to divide the rod into such segments of length dx, right? Length dx is to cover up the whole rod. So such a thing of length dx is at a distance x. So this length is dx, and this small element of length dx has mass dm. So this dm we can write lambda times dx, mass by length multiplied by length. So that means it is kx dx. Now you have to find the total mass of the rod. What is the total mass of the rod? Then you have to add up masses of these small elements, right? So each having mass dm. So you have to sum over dm or integration dm or integrate over dm rather. So integration of kx dx from, say, as you have seen, dm equal to kx dx. Here dm is equal to kx dx. So integration of kx dx from, see, you have to cover up the entire rod, so x will vary from 0 to L. So it's KL square by 2. total mass of the rod. Now this xcm is equal to integration of x dm divided by total mass. So integration of x dm means kx dx. Again x will vary from 0 to L divided by m. So there k will come outside. So integral x dx or integral x square dx is x cube by 3 with limit 0 to L. Now there I can substitute KL square by 2. So it's actually KL cube by 3 divided by KL square by 2. So this comes out to be 12 by 3. XCM will come out to be 12 by 3.